Is by Andrew Sale from Vanderbilt, and when is the automorphism group or right angle Artin group vast?
Okay, thank you, Ian, and thank you to the organisers for the invitation to speak. In particular, as you know, there's the conference dinner after this, so I'd like to thank the organisers for scheduling me to be talk number 23 and not talk number 24. That's a relief. Okay, so I'm going to start. I'm going to start my talk. I should say, first of all, everything is joint work with Vincent Girardel. I'm going to start my talk by stealing the start of somebody else's talk. So I learned a few things in 2016, and one of the things I learned is that if you steal from somebody else's talk, it can actually help you get somewhere in your life. So since the person I'm stealing from is sat in the audience today, I'll give him the credit. So this is, I'm sure you've seen this picture many times before. This is Brighton's picture of the universe of finitely presented groups. Or it'll be a smaller version of it. Where do we start? So perhaps I should let Martin do this since he's so if we start off with a point and take the fundamental group of a point, then you just get a trivial group. But we want some more interesting groups than this, so make our space a bit more interesting, make it a circle, and this is going to give us a group of integers. And then we can generalize this in two ways. Okay, we can either increase the dimension of the space we're looking at, so we can look at higher dimensional tori, and that will give us our free abelian groups. Okay, and then I've not really left myself enough space, but if you continue on, there's some other groups there, so nilpotent groups, solvable groups, and so on. And this branch is the amenable branch. In the other direction, if you, instead of taking a higher dimensional version of a circle, if you just take circles and form a wedge of circles, so a bouquet of circles, and look at their fundamental group, and you'll get the non-abelian free groups. And then generalize that, hyperbolic, semi-hyperbolic cat zero, and so on. And this is the non-positively curved branch. I'm not a good enough artist, so I'm not going to draw the line, but there is a line that lurks between these two. And what we really want to do is we want to understand this big void between these two classes of groups. How do they get on with each other? Okay, so one way, if we just focus on this portion of the picture, one way we can get from free abelian groups to non-abelian free groups is by looking at RAAGs. Okay, so these have been defined for us already this week. I'll just, for anybody who is maybe watching this on the video, I'll just write down my notation. So A gamma is going to be my RAAG. The generators are the vertices of this finite simplicial group graph, and two vertices will commute whenever they are adjacent in gamma. Okay, so they're connected by an edge. Okay, so those are the RAAGs. What we're looking at is not the RAAGs themselves, but we're going to look at their outer automorphism groups. Okay, so converting this picture into a picture for that, we'll have a similar kind of wedge-like picture. Our vertex, our point in this picture is now GL2Z, which is just out F2, and along the top we have GLNZ, and let's say n is at least 3 now, and down the bottom we have out of Fn. So in between, of course, we have out of a RAAG. That's one of many different ways you could go from one of these groups to the other. The aim is to kind of avoid the lion who's lurking somewhere around. Okay, so these are two classes of groups, obviously well studied. Analogies are often drawn between the two classes, and they share many properties. So they're in this picture, so they're finitely presented, virtually torsion-free, they're residually finite, they have finite virtual cohomological dimension, and they both satisfy Tits alternative. I think everything that I just said is also true for out of a RAAG. Okay, so the main references are papers by Charney and Vogtman, and Girardel and Levitt. They look more at automorphisms of free products. So if your graph, in your RAAG, if your graph is disconnected, then it decomposes as a free product. So this is very much necessary. And the Tits alternative, I should mention, because of these four people, nobody is in this room, but the Tits alternative, Camille Orbey studied this, treated this for the free products, and then completed it for out of the RAAGs using work of Charney and Vogtman. Okay, so those are things they have in common, but I'm more interested in things which are different for these two groups. So I was gonna say I'm gonna build a wall between these two groups, but apparently somebody is better at building walls than me. So I'm just gonna find the boundary between them. And the properties I'm going to look at, we can kind of vaguely call sort of vastness properties. So our ideal vastness property is the property of being large. So just to remind people, a group G is large if there's a finite index subgroup in G which admits an epimorphism onto a non-abelian free group. Okay, so another way to say this is the following. So for every finitely generated group H, you can find some finite index subgroup of G such that your finite index subgroup will map onto your chosen finitely generated group. So up to passing to finite index, you've got, you know, as many finitely generated quotients as you could possibly dream of. Okay, so how does this relate to this picture? Well, we can say it's well known that GLNZ for n, well, let's say GLNZ is large if and only if n is equal to 2. So if n is equal to 2, you're virtually free. Okay, in the other direction, looking at out Fn, well, we know this is large for n equals 2 because it's, again, virtually free, but it's also large for n is equal to 3. So this follows from, maybe there are other ways to see this, but work of Grunwald and Lubotsky, they developed these representations of finite index subgroups of out Fn. So for every n at least 2 and for every positive integer h, we take out Fn, you can find a finite index subgroup, let's call it G, and a representation of this finite index subgroup whose image is going to lie in SL n minus 1 times h of Q, and the image is commensurable to the integer points of this. So okay, so what this means in particular, if you take h is equal to 1, n is equal to 3, then you get a map pretty much onto SL2Z, which is virtually free. So this gives you the fact that you're large for out F3. Okay. Okay, but the question of whether you're large is still open for out Fn with n strictly bigger than 3. Okay, so in terms of this picture, we know what's happening up here, and we know what's happening for one step along this bottom branch, but then we don't know what's going on. So I mean, how can we hope to understand what's going on in the middle if we don't understand what's going on in the boundary? That's something I learned teaching calculus.
And your conjecture?
I refuse to. I'm not an out Fn person. So. Okay, so what we're going to do is slightly weaken this notion of largeness. I'll give you the following definition. So say a group G has all finite groups involved. Okay, if we take this line here, and instead of saying finitely generated, we replace it with finite. Okay, so if for every, say, F finite group, you can find some finite index subgroup such that this finite index subgroup will surject onto this finite group. Okay? So if you know you're large, then you know you have all finite groups involved. Okay. So where does that leave us in this picture? Well, it's not too hard to see. There are many classic results about finite index subgroups and quotients and normal subgroups of GL and Z. So I think you probably just need the congruence subgroup property to understand the finite index subgroups, and then you can see that you can't have all finite groups involved in GL and Z. Okay, but the opposite end of the spectrum, without Fn, this will have all finite groups involved. Okay, so I'll abbreviate to AFGI. Why is that? Well, if we look at this result of Lubotsky and Grunwald, if we fix n, we can let h get arbitrarily big, and we have a map, or a finite index subgroup of out Fn, which is going to map onto SL of a very large dimension, and then we can get to arbitrarily large alternating groups from there, and that's enough to give us that we have all finite groups involved. Okay, so this is implied by Grunwald-Slabowski. Okay, so the question is, GLNZ, there we don't have all finite groups involved, down here we do, where's the boundary? Okay, and that's what I want to explain in the next 45 minutes. Okay. So before I can state what the boundary is, I should give you some background about the automorphisms of RAAGs. So first thing to consider are the generators. Okay, so these were first described by Lawrence. So if you're familiar with standard generating sets for GLNZ or for AutoFN, then you'll see some similarities going on here. I'll start, so there are 4 different types of generator. I'm going to start with what is perhaps not the first one you're going to think of. It's what's called a partial conjugation. Okay, so what we do here is we take fix some vertex in your graph, gamma. What we want to do is we want to say, okay, we have V, let's conjugate some other vertex U by V. Okay, if we do this, then we're going to have to look at everything that's adjacent to U as well. Okay, so we have to preserve the commutator relations in the RAAG. Okay, so what this means is, if we consider the following picture, here's the star of V. Okay, so that's everything. Well, I'm only concerned about the vertices, so it's just everything that's adjacent to V, all vertices distant at most 1 from V. And we consider what gamma looks like when we delete this. Okay, so if it breaks it up into, if it breaks gamma up into several connected components, let's call one of these Z. If you try and conjugate something in Z by V, you're going to have to conjugate everything else in this connected component by it as well. But then when you hit the star of V, if you're in the star of V, you commute with V, so you can stop there. So this means we can define a partial conjugation as follows. So I'm going to write it like this. So the multiplier is going on top, the set we're acting on is on the bottom, and it's just going to conjugate anything in Z by V and fix everything else. Okay, so that's the first type of generator. Okay, the second type is a transvection. Okay, so so what is a transvection? Well, if you fix 2 vertices in your graph, I'm going to write it like this. So there are 2 types of transvections, left transvections and right transvections. A left transvection is going to send V to UV and fix all the other generators. The right transvection will just send V to VU. Okay, so we should be worried for a moment that is this an automorphism? Okay, for out of n, of course it is. But for the RAG, we should worry about preserving the commutator relations again. So let's think about that. So suppose we have some W which commutes with V. Okay, and W is not equal to W, not equal to V. Okay. So if we apply one of our transvections to this, we should still have the identity, right? So we should have 1 equal to, say, RUV of WV, but this is just W and then VU. Okay, so 1 is equal to the commutator of W and VU. Well, we know that V commutes with W, we're in a RAG, so this is only going to be true if W and U commute as well. Okay, so what this gives us is the following situation. So we started off by choosing W, which is in the link of V. Okay, so that's anything that's adjacent to V but not equal to V. And then we finished up by showing that W should commute with U. Okay, we didn't say it can't be U, so we just know that W is going to be in the star of U. Okay, so in particular, if we're going to have an automorphism here, we better have the link of V contained in the star of U. Okay, so we use this to define a partial preorder on the vertices of gamma. Okay, so we get a partial preorder, so we say that V is less than or equal to U if the link of V is contained in the star of U. Okay, and this is if and only if these transvections are going to actually be automorphisms. Okay, so those are the first two types of generators of out of a RAG. The other two types, what do we need? Well, we can invert one of the generators. So just invert one of the generators and fix all the others. Or, okay, in out of Fn we can permute a basis for Fn. Here we have the commutators to preserve, so we can do any graph symmetry. And this will give us an automorphism. Okay, now having told you those last two, I'm going to tell you immediately to forget them. So what we're going to look at is a finite index subgroup of out of a RAG, which is generated by the transvections and the partial conjugations. Okay, it's not hard to see that if you just take this subgroup, then your finite index. Okay, so we'll write out 0 of A gamma. This is the finite index subgroup that's generated by the first two types I mentioned. Okay. So we have this partial preorder on the vertices. Let's look more at that. Okay, so it's going to have equivalence classes. Okay, so we're just looking at anything which satisfies this. So u is less than or equal to v and v is less than or equal to u. This is something which can happen, and it'll give you an equivalence class for this partial preorder. Let's think about what can happen if you take an equivalence class. So if you take, let's suppose you have three vertices u, v and w which are in an equivalence class. So the definition says that the link of u is contained in the star of v, and the link of v is contained in the star of u. So that's what it means for u and v to be equivalent. Let's suppose there's no edge between u and v. Then what we're looking at, it's not hard to show that these two vertices have to have a common link. Okay, so if there is no edge in the equivalence class, then these will give you that they have equal link. Okay, so if you have no edges in your equivalence class, the links are equal. And furthermore, of course, if you look at the RAAG subgroup generated by the equivalence class, then you just get a free group. Like n is the size of the equivalence class, so we can call this, I guess that's going to be hard to see if I write down there. Okay, so we'll call this a free equivalence class. Okay, if there are no edges between the vertices in the equivalence class, it's going to be free. Okay, now what happens if we add an edge? Okay, so suppose we have u and v are now connected by an edge. Okay, now what's going to happen to this relationship? So we know that v is now in the link of u, which is contained in, so u is less than or equal to w, so this is going to be contained in the star of w. Okay, so v is in the star of w, which means we're going to have an edge here. Okay, and we repeat that, so u is in the link of v, which is in the star of w, we'll get another edge here. Okay, and we can keep doing this no matter how big the equivalence class is, we'll end up with a complete graph, we'll end up forming a clique. So what we end up with will be the RAAG generated by the equivalence class is going to be a free abelian group, so we can call this abelian equivalence class. Okay, if you have an abelian equivalence class, you can show also that every two elements in the equivalence class will share the same star. Okay, so in the free case, they share the same link. In the abelian case, they'll share the same star. Okay, so our notion of vastness that we're looking at, this notion of having all finite groups involved, it really focuses on the quotients of the group. If you want to think instead about subgroups, then you could ask, is the free group a subgroup of your out of a RAAG? Okay, and this was answered by Matt Day. So he said, out of a RAAG will contain a non-abelian free group if and only if either one of the following two things happen. Okay, so firstly, if you have an equivalence class of size 2 or more, then you'll have two transvections, and you can swap the multiplier in those. So you can look at, for example, this group generated by LUV and LVU. It's not hard to show this is going to be virtually free. Okay, whether you're abelian or free, your equivalence class. So this is virtually free. So the first case is that gamma contains an equivalence class of size at least 2. Okay, so that's how you can get a free group from transvections. On the other hand, we have this other type of generator, we have these partial conjugations. How can you get a free subgroup from those? The jargon associated with that is something called a separating intersection of links. Or SIL for short. Okay, so this is going to give you a free subgroup from two partial conjugations. So what is a SIL? Okay, so a SIL, we consider it as a triple of vertices. That's the way it makes sense for us. And we write it like this. So it's a separating intersection of links. So the idea is that one of the vertices is separated from the other two by the intersection of the two links. So the picture to have in mind is maybe here's X, here's Y, here's the intersection of their links. There's some other stuff going on up here. We need, it's not going to make sense, this definition, not grammatical at least. So we need the distance between X and Y to be at least 2, so X and Y do not commute. And then we have this property that if you want to travel from Z to either X or Y, you have to pass through the intersection of the links of X and Y. So any path from Z to XY must pass through the intersection of the links of X and Y. Okay, so now if you look at this picture, if you delete the star of X, you're going to have a connected component down here. Let's call it Z, big Z. So we can define a partial conjugation by X on Z. And we can also do the same thing for Y, because you delete the star of Y, and Z is also going to be a connected component of that. So we have both these partial conjugations. And if we look at what they generate, because x and y do not commute, it's not hard to see that this is going to be free group. Okay, so this is how you get a free group from partial conjugations. Okay, and I should add to the theorem, because I'm not doing day justice. The hard part is showing what happens when you don't have a free subgroup. Okay, so if you have neither of these two cases, then you can actually show that the group is virtually nilpotent. I think I need the word virtually. Yeah. So what happens if you don't have a free subgroup is out A gamma is virtually nilpotent. Slightly different. Okay. Okay, so the theorem with Girardel is the following. So we can say that the outer automorphism group of a RAAG has all finite groups involved, even only if one of the following properties occur in gamma. So there are three properties that could happen. So the first one is that you have a free equivalence class of size at least 2. So here need to be free. The second one is that gamma has an equivalence class either free or abelian, but it has to be of size precisely 2. Okay, and if neither of those things happen, then you can look for a CIL. Okay, if you have a CIL, and as Day showed, you will have a free subgroup, and you want to use that free subgroup to get all finite groups involved. Okay, and we can actually say more. If this doesn't happen, we can give some fairly rigid structure to the automorphism group, the outer automorphism group. Okay, so if this group doesn't have all finite groups involved, then there's a short exact sequence as follows. So in the middle we've got the finite index subgroup generated by transvections and partial conjugations. The quotient is a product of special linear groups SLNIZ. Okay, here, so each Ni is going to be at least 3, and it's the sizes of the equivalence classes that you'll have, the abelian equivalence classes that you'll have. Okay, so that's the quotient. So you have this finite product of SLNZ, and the kernel is going to be finitely generated nilpotents. Okay, so you've got this very nice structure for the group if you don't have all finite groups involved. So I'll say something about the proof of this now. Okay, so we'll look first at dealing with these first two cases. So when you have one of these equivalence classes. So this is perhaps the easier part of the proof. If you have an equivalence class in your graph, okay, then what you can do is you can take out of the RAAG, or the finite index out 0 of the RAAG, and you can construct an epimorphism onto the outer automorphisms of the equivalence class. So onto out, leave a 0 in there. Of the RAAG, and this, of course, is going to be equal to either, I should say, SL and the size of U, Z, or out Fn, or, well, not the whole of out Fn, but a finite index subgroup, which will map onto SL instead of GL. But if you throw the inversions back in, you'll get the whole of Fn from this.
Andrew, sorry, I should have asked you this before, but and maybe you said it in that situation on the right. Do you actually know what all the finite quotients of that guy are? In general, they can be quite complicated.
Well, you've just got a finite product of.
No, I'm worried about the extension by the nilpotent group. So if I extend, so SL, so for example, it's probably open whether, like, if I extend SL3Z by, I don't know, Pavel, is SL3NZ good or not? Is SLNZ good? Yeah.
3Z? No.
Yeah. So probably, like, when you extend SL3Z by an abelian group, it's probably not residually finite, for example. So it's not kind of in general for an arbitrary extension. So.
Okay, but this property of having all finite groups involved, it will pass to and from finite index subgroups.
Oh, so you've got enough just from there. Okay,
so, yeah,
you don't need to understand all the quotients.
Yeah.
Absolutely. Yeah.
So that's fine.
Okay. Sorry,
that's okay. Okay, so this lemma gives us a map onto either SLNZ or out Fn. So we can see from here, if we have one of these equivalence classes, we get a map onto a group that we understand with regards to having all finite groups involved. So out Fn has all finite groups involved, and GL2Z has all finite groups involved. And if you map onto a group which has all finite groups involved, then you yourself will have all finite groups involved as well. So a consequence of this is that 1 and 2 will imply that you have all finite groups involved. just a few words on how you do this. All you do is you consider a map as follows. So you go, move it the right way around. You first consider the map that kills any vertex that's not less than something in your equivalence class. Okay, so here I'm using this notation to mean the set of all vertices such that v is less than or equal to u. Okay, so this is a factor map, and what we're doing is kill any vertex that's not in this set. Okay, and then once you've done that, you can then restrict. Okay, but you have to check when you're trying to restrict. You have to check that the conjugacy class of the equivalence class is going to be preserved. Okay, and you can check that in the image of this. That's what happens. Okay, so that deals with the first two cases here. Okay, so now for the third case, when you have a sill, we actually get a stronger result than just having all finite groups involved. So we have the following proposition. So suppose all equivalence classes in your graph are of the abelian type. Okay, and suppose that you have a sill. Okay, if you have these two properties of the graph, then your outer automorphism group is going to be large. Okay, so this means you have all finitely generated groups involved. It's much stronger in that sense. Okay, and this is what is the harder part. There's more involved in this. Okay, so just to give you the idea of this, we're kind of mimicking what we did for this lemma earlier. So the first step though is to find what we call a special sill. Okay, so this is going to be in some sense minimal for inclusion, I think. But it's some particular sill which allows you to do the following. So if you let, well, let's give the sill a name, so let's call it the vertices x1, x2, x3. If you let S be the union of these three equivalence classes, and what you can do is you can go from out 0 of the RAAG, and you can map to probably the 0, well, it doesn't matter, out of the sill. Okay, so what is this going to look like? Well, the sill It's going to have x1 and x2. Remember that these give you a CIL, so part of the definition is that they do not commute. And they also won't commute with x3. So what you're going to have is out of free products of three free abelian groups. So Z, say N1. Okay, so here Ni is the size of your equivalence classes. Okay, so first thing to note about this map is it's not going to be surjective. Okay, that's part of the problem. I'll say a little bit more about the image in a minute. Just say how we construct this map. It's the same kind of thing that we do here. So we first go to the out of anything that's smaller than or equal to something in the CIL, and that's by the same process of killing anything that's not there, any of the vertices that are not there, and then we can restrict. Okay, and where we need this special CIL here is that this restriction is going to be well defined. Okay, so by choosing the right CIL, this map, the image of this first factoring map is going to be contained in a set of all outer automorphisms which preserve the conjugacy class of the three equivalence classes in the CIL. Okay, so this special CIL enables us to define this map. Okay, so the image what do we know is going to be in the image? Well, we started with a CIL, so we'll have the partial conjugations from the CIL which gave you the free subgroup. So those I'll just call I'll just write like this. So if your equivalence classes x1 and x2 have more than one element in each, then you'll get more partial conjugations than this by changing the element in the conjugacy class. But let's, for simplicity, we'll assume that each equivalence class is size 1. Otherwise things get a lot more messy. So you'll definitely contain these two partial conjugations, whatever happens. Maybe you'll have the third partial conjugation, so acting by x3 on either x1 or x2. So remember, we're in the outer automorphism group, so it doesn't matter which you act on here. This is going to be equal to, or after taking an inverse, it's going to be equal to cx3, x2. So you might have this third partial conjugation. Maybe you'll also have some transvections according to whether or not you have any. So maybe you'll have some of these partial conjugations and their corresponding right transvections. So let me just say briefly, if you have the third partial conjugation, so if you have all three partial conjugations in the image, then the way that we showed that your large is by going from this group, this product, out of a free product of three abelian groups to PSL2Z. So the lemma or proposition or whatever. So if you have a subgroup of such a group, and if it contains all the partial conjugations that it can contain, then H is going to be large. Okay, and to briefly give you an idea, if you're familiar with these representations of Grunwald and Lubotsky, what we do is we generalize these. Okay, so I don't really have time to say very much what you, I mean, if Ni is all equal to 1, then you're looking at out of the fundamental group of 3 circles. And then what you want to do is you want to take a finite cover of this bouquet of circles. So something like, if I can get this right, so that should be a twofold cover, which you get by mapping each generator to the generator of Z2. And this, if you look at the automorphisms which fix the vertices, which preserve this and fix the vertices on this graph, and then you get a finite index subgroup of out F3. And what you need to then check is you act on, we call this space X, you act on the first rational homology of this space, but not all of it, because it's going to decompose with the action of Z2. You'll have an eigenspace for 1 and an eigenspace for -1, and the -1 eigenspace is going to have dimension 2 by a classic result of Eschertz. So that applies when you're looking at Fn. V1, V-1, sorry, is going to be q to the n-1. That's where the n-1 comes from in the Grunwald-Lubotsky theorem. Okay, what we have to do is we have to, instead of taking a bouquet of circles, we have to take a bouquet of tori and glue them together and do a similar kind of strategy and understand what the homology is and so on. On the other hand, if you don't have this partial conjugation, the method is different and technical and not so interesting to give in a talk, and I haven't got time either. So let me just finish the last few seconds by saying that in the theorem I stated you can replace this property of having all finite groups involved with other properties. Okay, so you need a property which is going to be true for out Fn, false for GLNZ for n at least 3. You need it to be able to go to and from finite index subgroups. You need a couple of other things. You need it to be inherited from quotients. And then there's one, I think there's one more short exact sequence condition. But properties which satisfy this include property of being SQ universal, property of, let's say, not being boundedly generated, okay, and the last one, it's related to Alessandro's talk, which I think was yesterday, but I've lost track of what day it is. It's what we call having virtually many quasimorphisms. So virtually means you can pass to a finite index subgroup, and then you look at the, borrowing Alessandro's notation, the space of homogeneous quasimorphisms of this finite index subgroup is infinite dimensional. Okay, so if you take the statement at the top here and replace all finite groups involved with any of those, and it's still going to be true. Okay, so I'm over time on that clock and I'm over time on that clock, so I have to finish. Okay, thanks for your attention.
Still time for a couple of quick questions,
So going back to the largeness property, have you reduced largeness to understanding largeness for out, F4, and so on?
Yeah, so it is a consequence. If you believe out Fn is always large for all n,
And it satisfies what you
then
it's one of those.
yeah, just from the lemma which I've erased, because you map onto out Fn,
Yeah, right.
as largeness is going to be inherited by out to the right. So if
But what with the third case, if not all classes are abelian?
so the third case, well, if you don't satisfy case 1 or case 2, then in particular, if you don't satisfy case 1, all the equivalence classes are going to be abelian.
There was a proposition that said that on the sill.
And then
Yeah, okay.
the proposition which is erased gives you that you're large, yeah.
Okay, so if we're out of questions, let's thank Andrew and thank all of the speakers for this afternoon.